Take a look at this RGB LED smoothly fading between colors. We are running this entire sequence using a single data wire. To pull this off, we need to master a technique called pulse width modulation, or PWM. It allows us to output analog-style signals from strict digital pins. You will need a few pieces of hardware to follow along: an Arduino Uno, an I/O expansion shield, a digital RGB LED module, and a 3-pin cable. The DFR robot kit includes all of these. Controlling 3 distinct colors, red, green, and blue, with only one wire keeps our physical build incredibly simple. We rely on a clever software protocol to do the heavy lifting. Standard digital pins have a strict hardware limitation. They operate in exactly 2 states: 0 volts, which is off, or 5 volts, which is on. There are no intermediate levels. Pulse width modulation solves this. We simulate those in-between power levels by switching the pin on and off extremely fast. This chart shows how the code translates to voltage. When we write analog write 255, we create a 100% duty cycle. The signal stays high the entire time, delivering maximum constant voltage and full brightness. If we drop that value to analog write 127, the duty cycle becomes 50%. The rapid on and off switching creates the physical illusion of half brightness. Keep in mind, not all digital pins support this feature. Look closely at your Arduino board and locate the small tilde symbol next to specific pins. Only those pins are PWM capable. PWM does not provide actual variable voltage. It is a high-speed illusion that lets microcontrollers dim lights or precisely control motor speeds. Let's set up the hardware. Connect your I/O expansion shield directly onto the top headers of the Arduino Uno. Next, take your 3-pin cable and plug the RGB module strictly into digital pin D3. Your wiring needs to follow this exact sequence. Connect the green wire to the signal port marked DI. Connect the red wire to the 5-volt VCC port. And connect the black wire to the ground port. Double-check these connections. Swapping the VCC and ground wires will cause the LED to fail and could potentially short out your board. This specific LED uses the NeoPixel protocol. That protocol dictates exactly how our single green signal wire can carry distinct instructions for red, green, and blue all at the same time. A precise physical setup is required before complex software protocols can function correctly. Open your Arduino IDE. Before writing anything, ensure you have the Adafruit NeoPixel library installed so the software can talk to the module. Every Arduino script requires 2 non-negotiable structural blocks: void setup and void loop. The setup function is your preparation phase. It runs exactly once to initialize the LED. The loop function is the execution phase, running the enclosed code continuously, forever. Our script relies on a custom routine called fade in out. It steps a numerical brightness variable from 0, meaning off, up to 255, which is maximum brightness. We automate that fading process using a for loop. The initialization variable starts at 0, checks a condition, and then incrementally increases the brightness step by step. Watch out for the most common syntax error, missing a semicolon at the end of a statement. Also, verify your open and closed curly braces are perfectly balanced. An unbalanced bracket will stop your code dead in its tracks. Your script will only compile successfully when you combine the overarching logic of the loops with strict adherence to C++ punctuation. With the code written, click the Upload button in the IDE to compile and push it to the board. Look at the tiny RX and TX lights on the surface of your Arduino. They will flash rapidly, confirming the data is transferring. If the upload completes but the LED remains dead, start with your hardware. Verify that the signal wire is strictly seated in pin D3. For software troubleshooting, check your logic. Ensure any custom analog write command values are strictly bounded between the 0 and 255 limits. Seeing the hardware respond exactly how you programmed it is the definitive test. You have established a working bridge between digital commands and physical reality. Watch the final result. Because our PWM frequency is switching so incredibly fast, the color transitions appear completely fluid. Take some time to safely experiment with the code. By altering the numerical mixing variables inside the fade-in-out function, you can invent your own custom colors. If the programming structure felt overwhelming today, stick with it. In the next lesson, we will do a deeper dive into the foundational logic operators and core math concepts holding these scripts together. You have successfully forced a strict binary on and off digital pin to speak in the fluid analog language of light.